Hello and welcome to today's third conference of Forum MobiliT.AI 2021. Today for this third conference, we have the pleasure to welcome Edouard PAUWELS. Edouard is an assistant professor at Université Toulouse 3 Paul Sabatier. He also works at the Institut de Recherche en Informatique de Toulouse in the Argumentation, Decision, Reasoning, Uncertainty, and Learning team. His research focuses on numerical optimization, its applications in artificial intelligence, and the guarantees it can provide. So today, Edouard is going to talk to us about algorithmic differentiation for AI. And so just before it starts, so if you have any questions, so you can ask your questions anytime in Swapcard using the Q&A functionality. And so without further ado, Edouard, the floor is yours.
Thank you very much, and thank you for the introduction, and thank you for the organizers of this very nice event to let me talk here. So indeed, I'm going to talk about algorithmic differentiation in artificial intelligence. And before starting, so this is a collaboration, an ongoing collaboration in ANITI project, which is an artificial intelligence project in Toulouse, in France. And my collaborators are Jérôme Bolt from Toulouse School of Economics and David Bertois and Sébastien Garcinovich from IRT Saint-Exupéry. That's the plan. First, I will wrap up notions of derivative and how they occur in AI. Then I will talk about non-smooth algorithmic differentiation and explain why it induces some spurious behavior, some artifacts. Then I will present a mathematical model which describes those artifacts and some results related to numerical optimization and learning. And I will finish with some experiments. Okay, so let's start with derivative. What is a derivative? So the usual definition of a derivative is through best linear approximation or best affine approximation. So there is a function f, which we need to approximate around a given fixed input x bar here. And we also approximate it by an affine function. So the function f is approximately equal to this quantity here, which is affine in y. So affine means linear plus constant. And indeed, the dependency in the variable y here is linear. And the linear part is determined by this quantity, which I call the gradient. So I will use gradients, derivative or Jacobian quite interchangeably in the presentation. So this allows, for example, to draw a tangent to a curve in dimension 1, or to obtain the tangent plane to a graph in higher dimensions. And the idea is always the same. The direction of the plane or the curve is obtained by the derivative. It's related to the derivative. Okay, so that's a nice mathematical concept, but why do we need derivatives in artificial intelligence? Why are they important? So the first thing is that neural network training most often reduces to numerical optimization, and this is most often performed by gradient methods. So derivatives are used simply to train neural networks. So that's one thing. Another context where you might need derivatives, sensitivity analysis. For example, if you want to measure importance of certain features, then having access to derivative might be helpful. And there are possibly other situations for which derivatives are needed, and you can think about them. So the question is, how does this derivative occur practically? How do we manipulate them practically for a neural network? So let's dig a bit into what it means, a neural network. Okay, so it's an input-output system. The input variable here is copied on an input layer, and the output will be output layers, and the intermediate layers will be hidden. So what is relevant here, what is important, is the relation between consecutive layers. So it takes place as the composition of an affine transformation. So here W and B are matrix and vector. So this is an affine map. It's a simple map, it's affine, which is composed by a nonlinear transformation. And this is potentially more complicated. So this I will call activation function. So the set of W matrices and B vectors are concatenated into a parameter, which I call theta. And those are the parameters of the network, or the weights of the network, if you like. So those are the ones that we want to tune. When we perform learning, those parameters are tuned in order to the network to reproduce some behavior that we wanted to reproduce. And this is performed through optimization. If you fix the parameters, okay, if you fix f theta, then you have an input-output relation. So this is a function, and the network is simply a parameterized class of function described by those weight parameters. So you may either describe it by the for loop here, or equivalently by the complicated composition that you have here. But the only thing you need to remember is that neural network is simply a parameterized class of functions. Okay, now if you want to train this network, you need to compute gradients. Okay, so you need quantities like this, the derivative of the output of the network with respect to the parameters theta. And this structure is a bit annoying. It's a bit complicated, and definitely you don't want to compute this gradient by hand. Okay, the structure is complicated, and so there is a numerical device called backpropagation. So what is backpropagation? It's an occurrence of algorithmic differentiation, and it's an automatized numerical implementation of the chain rule of differential calculus. So we have rules to compute the derivative of a composition, provided that we know how to compute the derivative of each element of the composition. And backpropagation implements those rules in an automatic fashion. Right, so let's wrap up about neural network. Neural network recipe is first defining a structure and define activation function. So describe your neural network. And most often this is done by writing a numerical program. Then there is this backpropagation device, which essentially enforces that what can be programmed can be differentiated, and your derivatives can then be used for training using optimization, or if you like, for sensitivity analysis. And so this idea of automatically computing derivatives is at the heart of very popular numerical tools to manipulate neural networks. Okay, so that's first idea. Let's talk about non-smoothness. So it turns out that one of the most widely used activation functions, so those nonlinear functions which occur in the network, among them, the most widely used is the positive part, or the ReLU function. This is how it's called in this literature. So here I give you a program which computes the function and a graphical representation. And so there is a kink here, which means that it's not differentiable at zero. There is no notion of best tangent, best affine approximation at zero. So let's see how the computer differentiates this at zero. And the examples that I'm describing here are given by Tensorflow. So that's what the computer does. That's what Tensorflow does. You have these if-else statements. You need to differentiate through it. And so this has two branches. And essentially what Tensorflow does is differentiate the active branch. So in particular, if you choose the input to be exactly zero, the active branch at zero is zero, and the derivative of zero is zero. So that's how ReLU is differentiated. And you can then combine it in the backpropagation framework with other operations and propagate compute derivatives using the chain rule of smooth calculus. And you just pretend that ReLU is smooth and that its derivative at zero is zero. So this is nice, but it has some drawback, and is depicted in the picture that you have here. So this is a function, and I call it zero. Okay, and the reason it's called zero is because it computes zero. So the output of this function is constantly zero. That's a nasty implementation of the zero function, if you like. And if I ask TensorFlow to differentiate this function, then it will tell me that the derivative of the function is most often zero, but at zero, it's computed to be one. Okay, so you can try it on your computer. The derivative here is one. And this value one doesn't have any meaning from a mathematical perspective. Okay, it's a pure artifact. It's not a numerical error. It's not a programming error. It's just that we apply brute force rules of differential calculus to non-differentiable objects. And this is an occurrence of the following idea. Algorithmic differentiation, or backpropagation, is an operation on a program, not on the function itself, but on the program. What it means is that the function is given in the form of a composition, and in a non-smooth context, if you change the composition, even if the output function is the same, then the derivative may change. And you may play with this further and modify the value of computed derivatives at prescribed input points in a more or less arbitrary way. So this is an example with the sine function. So this is really annoying because, for example, here I set the derivative to be zero artificially at prescribed points. Those are represented by the blue dots. And so those zeros correspond to a fixed point of the gradient iteration. If you are not lucky and if you initialize your gradient descent recurrence at this point, then the algorithm will not move simply because it started on an artifact and the artifact tells it not to move. So let's wrap up non-smooth algorithmic differentiation. So backpropagation, again, is an efficient implementation of the chain rule of differential calculus. And as such, its validity domain is the same as the validity domain of this chain rule. So it's restricted to differentiable functions. In practice, this is used a lot with non-smooth functions. And as we have seen, this is a source of pathological artifacts. So the starting motivation for this study, for this work, was to understand the backpropagation in the non-smooth context, to understand the potential artifacts, and to study their impact on first-order optimization algorithms, remembering that those are the most widely used tools for neural network training, for example. And if there is one thing that you need to remember from the presentation is the following. Algorithmic differentiation is an operation on programs, meaning on functions given in the form of a composition. So it's an operation on the composition and not on the function itself. Right? Okay, so let's see some theoretical results that we obtained. First, let's give a mathematical model for algorithmic differentiation. So to build this model, we will need some elementary function. I call them elementary log x functions. Those are the nice functions, okay? And we choose nice functions to be defined on a full Euclidean domain by, let's say, a formula, a compositional formula, which involves polynomials, logarithms, and exponentials. So this captures a lot of the smooth function that we have in machine learning, and potentially the majority, virtually the totality of them. And those are the nice functions. So to define a class of non-smooth functions, non-differentiable functions, we will use a finite number of nice functions. So I will choose m of them. And I will define a continuous non-differentiable function by a selection process. So there is a second function, which I call s here. And s takes values in the integers from 1 to m. So essentially, s is choosing among the m function that we have here, which one is active, right? And there is further hypothesis on s, but this is technical. So why do we choose this representation? Essentially, it's a model for a program, right? So if you have a P, a program for a function f, so the same example as what we had before, you have the ReLU function, you have a program for the ReLU function, then P actually induces a selection index here, right? So we have two branches, and the if-else statements induces a selection between the zero function or the identity function, which are the two possible outputs. And alternatively, conversely, we may say that S is a mathematical model for P. So this is just an abstract way to think about programs. But with this abstraction, we can describe what backpropagation actually does, okay, in a non-smooth context. So it's the same setting. If you have a numerical program for F, then this program will induce a selection index. So the selection index doesn't need to be known explicitly. It's just induced by the program. Okay, so the program, we know that the program induces this index. So what does backpropagation do? Simply, it provides the output as an output, the derivative or the gradient of the function which corresponds to the active index. So remember that the m function that we had here are nice. Okay, they are among the nice functions. So I have a derivative for them, and at each point x, I have an active index, and I compute the gradient of this one. Okay, and this really corresponds to what we had in this picture. So for the ReLU function, we had two possible outputs, right? And at 0, the active branch is 0. So backpropagation applied to 0 outputs 0. Okay, so based on this representation, we introduced a notion of conservative set-valued fields. So this is a mathematical concept which was introduced in order to capture those artifacts induced by algorithmic differentiation in a non-smooth context. So I'm not going to describe what it is, what it means. It's too complicated, but I'm just going to describe some of the results that we could obtain using this concept. So again, we may think about a program inducing a selection index representation for a function f. Okay. So in this case, it holds that backpropagation applied to program has to compute a gradient almost everywhere. So the precise meaning of almost everywhere is I mean, there is a mathematical statement behind it. I'm not going into the details, but essentially it means that the set of inputs where this doesn't occur is negligible. Okay, so we essentially don't see it. So backpropagation is right the majority of the time, and it computes the actual gradient. We also investigated neural network training. So SGD is stochastic gradient descent, and it's among the most widely used algorithms for neural network training. So the thing that we could do here was to define an optimality condition. So this is, if you like, a generalization of the optimality condition, which says that derivative has to be 0 at local minima, for example. That's a generalization of the usual optimality condition. And we could prove that sequences generated by SGD in a learning context are attracted by the points which satisfy this optimality condition. So this is a satisfactory result because we could characterize the limit points of SGD sequence in this context. Among those limit points, we have artifacts. So if you remember these pictures, we have zeros, but those zeros are artificial. So if you initialize a gradient descent algorithm at this point, for example, then the algorithm won't move because the computer tells him that the derivative is 0. So it's a fixed point, it doesn't move. And this is completely artificial, right? There is no reason why it should not move. This is not a minimum, for example. So the thing is, if you are extremely unlucky, you may initialize on those points, and so the theory has to account for them. So that's a part of this result. But then we may ask the question, does it occur often? Okay, do SGD sequences or sequences generated by learning algorithm converge to those artifacts often or not? And the answer turns out to be positive in this case, meaning that most SGD sequences, so there is a quantification of this, what this most mean, but majority of SGD sequences, so generated by learning algorithm, are attracted by usual optimality conditions. Usual means that they actually don't see the artifacts here. They converge to points which satisfy a true optimality condition, let's say. So that's what the theory that we had. Let's confront the theory to experiments. Okay, and we will do this by asking the following question. We have seen that TensorFlow chooses the derivative of ReLU at 0 to be 0. Why should we choose this? Okay, this choice is arbitrary. First, if I give you a different program for the ReLU function, then the value of the derivative at 0 would change. So if I put a strict inequality here, at 0, the active branch changes. It's not 0 anymore, it's the identity. And so the derivative of the identity is 1. Okay, so I could simply change it by implementing the ReLU function in a different way. So in order to describe the experiment that we did, I introduced this notation. Backpropagation underscore S will be backpropagation applied to a neural network, say, but enforcing that the derivative of ReLU at 0 is S. It's not 0 anymore, it's a parameter S, and this one is fixed. Okay, think about a fixed value. And what the theory of conservative fields says, so the elements that we have introduced before, it says two things. First, the choice of S should not have any impact almost everywhere. So it means that the arguments, the inputs for which the choice of S has an impact is actually negligible. And the second thing that it says is that most learning sequences produced by learning algorithm using SGD should not be affected by the choice of S. So the choice of S should not have an impact on those sequences. So let's check it. It's something that we can check practically. So in order to do that, we consider a very simple neural network architecture. We generated two SGD sequences. So they are the same, they have the same at initialization. And then the only difference between the two sequences is that is the value chosen for the derivative of ReLU at 0. So that's the only thing that changed. And the theory says that the sequences should be the same. Okay, this should not have an impact. And this confirms the intuition as most of the researchers to whom I asked about this question told me that this should not have an impact. So we performed this experiment, and the result was quite surprising. Actually, there was a difference. Okay, there was a difference between the two sequences. So what is represented here is, if you like, the distance between those two elements as a function of k. So iteration counter is k here. So as you see, it starts at 0 as theory predicts, but at some point there is a jump. And after this jump, there is a smooth increase of the difference. So it actually has an impact. We investigated a bit further. And so here what I'm depicting is a certain quantity that is also evolving as a function of k. The precise definition of the quantity is not so important. What is important is that this is an argument of the ReLU function somewhere in the network. So somewhere in the network, we compute ReLU of this quantity and also ReLU prime of this quantity. Okay. And if you look at this place precisely, which corresponds to the bifurcation here, there is a sudden drop, and this drop corresponds to ReLU evaluated exactly at 0. So at some point during training, there is an argument of ReLU which is exactly 0. And so we compute ReLU of 0, but also ReLU prime of 0, and this explains the bifurcation. There is another way to show the same idea. So that's a graphical representation of a neighborhood of the point where the bifurcation occurs. And the quantity that is represented here in the plane is the same type of quantity. So it's an argument of the ReLU function. And we see that in this plane, the white area corresponds to inputs for which the derivative, the argument is exactly 0. So it's a numerical 0. It's not a 10 to the minus 8, it's 0. Okay, so what's going on here? Those experiments were performed in 32 bits precision floating point arithmetics. This is the default precision in PyTorch. So all this was performed in PyTorch, but it's also the default in TensorFlow. And in 32 bits precision, the precision threshold, the epsilon value, if you like, is close to 10 to the minus 8. Okay, so here the arguments are close to the precision, and at some point, one of them is 0. So this suggests that this is related to numerical precision. And if you perform indeed the same experiment in 64 bits precision, then you don't see the bifurcation anymore. And this argument is still of the same order of magnitude, but you don't have the drop here, which means that since the precision threshold is much lower, we are able to carry out the computation accurately. And this is a representation of the same quantity and the same neighborhood. And you see that it's much smoother than when we could have in 32 bits, for which we had exact zeros. Here we don't have exact zeros anymore. So that's a precision issue. Let's push those experiments further. So we considered a fully connected network on MNIST dataset. So this is a very standard setting. So theta are the network parameters, and here we assume that they are random. We choose them randomly, uniformly over a box. F theta is the training loss related to this problem. And what we try to estimate is the probability that the backpropagation changes when we change the value of ReLU prime at 0. Okay, we want to estimate this probability, and the randomness is over the random draw of the parameters, so the weights of the network. And again, the theory predicts that this probability should be 0. Okay. And if we perform these experiments, we get the following results. So depending on the precision, in 16 bits, we find a difference 100% of the time. So that means that 100% of the time, I think that there are 1,000 draw of the parameters here. 100% of the time, there is at least one element in the data set for which there is a difference. In 32 bits, this drops to 24%, and 64 bits, 0%. So this confirms the intuition that we had before. This is related to numerical precision. The question is now, does it impact learning? Okay, so does it have an effect on the prediction accuracy of a network? So we consider a standard convolutional network and a CIFAR10 dataset. And that's the result that we obtained. Okay, so on the x-axis, you have different values for ReLU prime of 0, the derivative of ReLU at 0. And on the y-axis, you have test accuracy, which is a measurement of the prediction accuracy of the dataset. So the box plots account for different repetitions of the experiments. And what we clearly see in blue here is this kind of bell-shaped curves for which the maximum is around 0. So this suggests that the default choice for the value of ReLU prime of 0 is actually the most stable. Okay, and indeed there is a maximum, and then there is a decrease when we change this value. A second finding that we had is that if you combine this this change of the derivative of ReLU at 0 with batch normalization, so that's the curve above, then not only the test accuracy increases, but the dependency in the value of ReLU prime of 0 is filtered out. Okay, so this is an argument for batch normalization enforcing stability in training. Right, so let me conclude. So the starting point of this work was about derivatives which are ubiquitous in AI. They are computed using a tool called backpropagation. So this is a way to have access to them automatically. However, in practice, backpropagation is used outside of its domain of validity, which is restricted to differentiable functions. Crucial observation is that in this context, non-smooth backpropagation produces artifacts. So we built a mathematical model, and we found that theory confirms the intuition that those artifacts, due to non-smoothness, should have a negligible impact. However, when we confront this theory to real experiments, then we see that artifacts cannot be ignored because negligible sets may actually be fattened by rounding errors due to numerical precision, and so become visible, because this is a numerical precision issue. So future works include investigating applications which will be sensitive to those backpropagation artifacts, develop further the theory in order to understand the potential impact, and validate theory on empirical experiments. And if it turns out to be an interesting idea from an application perspective, maybe build numerical libraries which are more robust to non-smooth spurious behavior of algorithmic differentiation. So let me stop here. I thank you for listening, and if there is any question, I can try to answer.
Thank you, Edouard. Yeah, as well, there's thank you for the presentation. So there already is a couple of questions. So we have a couple minutes left, so we can take maybe one or two questions. So first question, I guess this question came during the third part of your talk, and the question is, can the framework be used for discontinued activations?
Yes, it can. Be used for discontinuous activation. So it can be used to describe what backpropagation does for discontinuous activation. However, our theory does not translate for discontinuous activation. So you can use it, but we don't have the theory for this, and this is our ongoing work. And we have like ongoing work, so both theory and experiments related to discontinuities. Okay,
thank you. The second question, what kind of network did you use for the simple experiment? And have you observed any difference between the simple experiment on PyTorch or TensorFlow?
So the simple, all the final experiments were in PyTorch. The network for the simple experiment was, it was MNIST dataset, and it was also a fully connected network. I don't remember exactly the size. But not so big, right? So the simple experiment was performed on MNIST dataset in PyTorch with 32 bits precision and a network which was similar to this one.
Okay, so we have still 1 minute left, so maybe one last question. So what is the order of magnitude of the variation of the backpropagation? So for example, for 16 bits floating point precision, is the difference visible in 16 bits as well?
Yeah, so the difference, the order of magnitude of the difference is it's of the order of this jump, right? So here the order of magnitude is much above the norm of the actual gradient. I don't have any figure or any picture depicting the order of magnitude of the difference relatively to the size of the gradient or anything else. And this is something that we need to include in the work, and this is ongoing.
Okay, maybe just one last quick, any connection between backpropagation and subgradients?
Yeah, there is. So actually, if you have what backpropagation is computing is actually a subgradient of ReLU. So there is a very strong connection. The idea is that subgradients are not compatible with calculus. So you cannot, in the non-convex world, you cannot do additions, you cannot do compositions. You don't have calculus for subgradients. So this is why we introduced a new model to capture calculus applied to subgradients. But in practice, you're right, I didn't want to enter this detail because it's technical non-smooth analysis. But subgradients, I mean, the actual thing that is used to differentiate elementary non-smooth functions are subgradients, of course.
Okay, thank you, Edouard. So I think it's now time to switch on to the next conference. So thank you, Edouard, for the presentation.
Thank you.
Thank you, everybody, for attending. And please be reminded that the lab discussion is still live on Swapcore. So if you have any questions to ask Edouard, you can still use the chat tab and questions tab, and he will be able to answer questions. So thank you, Edouard, and bye-bye. Have a good day.
Thank you.